Okay guys, in this one I'm going to talk about more about wave-particle duality. It was probably more particle as a particle on a wave rather than light as a particle on a wave. I'm going to talk about the Davisson-Germer experiment, which I've drawn beautifully over here, and the de Broglie or de Broglie or that wavelength. So this guy was a physicist, and he hypothesized that the momentum is related to the wavelength for objects. So anyway, Davisson and Germer set up this experiment where they were firing electrons from an electron gun at a crystalline structure like this down here, so not to scale obviously. And what they were doing is looking at the diffraction pattern that they were getting reflected back off of that. So they had a 0th order maxima here, and they had a 1st order maxima here, and they looked at the spacing of the structure and compare that to a diffraction grating. And then they looked at the I guess momentum of the electrons that they were shooting out of their electron gun, and they graphed their results, and they actually kind of confirmed that in terms of light, d sine theta equals m lambda, but also in terms of particles, d sine theta equals m lambda. So you can same deal, sort of diffraction grating, or they were doing X-ray crystallography, so the crystal structure gave them the diffraction grating value, and they're actually looking at sine theta against lambda and confirming this equation, which kind of showed that particles had wave-like behaviour rather than waves having particle-like behaviour. So photoelectric effect, Einstein, onto a winner there. Light behaving like a particle, here particles behaving like waves, which is kind of cool. So the other cool thing about this is we know that P equals mv, so in terms of lambda equals h on p, we can look at lambda is h on b, probably, therefore P is h on lambda, therefore P is proportional to 1 over the wavelength. So I can look at this sort of experiment here, and we can sort of theorize or hypothesize or show that the momentum is proportional to the inverse of the wavelength. So as the momentum goes up, the wavelength goes down. And if momentum's going to go up, we're looking at the speed. So there's a particle, they have mass, they have a lot, the electrons, they don't have a lot of mass, but they have some. The speed is proportional to 1 over the wavelength. Now, with visible light, so with blue, we're looking at a minimum wavelength somewhere around the 400, probably closer to 410, 420. And what that means is that any surface that we look at that's got a spacing, sort of scales, scratches, hair follicles, whatever it is across the surface, that is the best resolution we can get. And that's as small as we can see with an optical microscope. With this idea, with this experimental proof from Davisson and Germer, using the de Broglie, whatever his wavelength, here's the name again.
De Broglie.
What we can do is ramp up the speed and decrease the wavelength significantly. So we're able to look at stuff that's 1,000 times smaller, I guess, than this. So we can look at stuff that's like fractions of nanometers now, rather than really big stuff. If I remember to, I'll put some photos around the screen of stuff that we've used, stuff that we've looked at using this kind of idea. We use this in something called an SEM, a scanning electron microscope, where you have your sample that you're looking at being, in this case here, the crystal structure, being passed across, forwards and backwards across a platen, and this beam of electrons fires down, and the diffraction pattern is measured off of it, so it can kind of resolve or plot in an image, I guess, what's going on. So it scans forwards and backwards across the image, much like your old reprojection TV does, or your current TV does. It basically redraws the picture, refreshes all the time. Similar sort of idea. So all we need to do is have a potential difference on our electron gun, and we wind that potential difference up, which increases the speed because of the work done on the charges inside the electron gun, which decreases the wavelength that we're looking at. These aren't in real colour. Sometimes you'll see scanning electron microscope images that are coloured. It's actually a false colour. They're actually all grayscale by default, because that these things have wavelength fractions of nanometers, or small chunks of this. So blue is the smallest color we can see. Computers and whatever can see a lot smaller than that. But this was a really nice sort of way of looking at the wave-particle sort of light-particle duality debate, where here we've got particles behaving exactly like waves, and Einstein's looking at waves behaving kind of like particles. So there's a nice little bit of symmetry in physics here.